Welcome to this session on sustainable energy systems and thermal transport. This is Professor Xiulin Ran from the School of Mechanical Engineering. I'm really happy to serve as a moderator for this panel, in addition to a speaker. So we're going to have, my pleasure also to have Professor Shweta Singh, Professor Rakesh Agrawal, Professor Rebecca Sees to join me to give an overview of our research. So we're gonna each present an overview of our research, and then please hold your questions till the end, but feel free to ask questions in the chat box. We're gonna answer those questions when all the presentations are done. All right, thank you. So we'll start with myself. I'm gonna share my screen. I have a short presentation here. Can you see my screen now? Can anybody confirm with me?
I can see it. Yes.
Okay, great. So let me enable the laser pointer. Okay, again, this is Xiulin Ran from ME. I'm gonna talk about our thermal transport and sustainable energy in my lab. So the topic one I'm gonna cover is radiative cooling nanocomposites. So you might heard a lot of times from recent news that Antarctica logs highest temperature on record in the history. The icebergs melt, and polar bears lose their homes. So clearly we are facing a challenge, a severe challenge on the global warming and the climate change. So how do we do about it? One target area can be air conditioning. We know conventional air conditioning, they use electricity to move the heat from inside the house to the outside. However, this heat is still kind of leaves on the earth, and that results in the heat island effect in urban cities, as well as contribute to global warming. Okay, we ask question, is there any way to dump the heat to deep space rather than leaving on the earth? So our approach is passive radiative cooling nanocomposites. So we developed this coating, which is basically a polymer embedded with nanoparticles with different shapes and sizes, and you see. So what this coating does is reflects almost 100% of the sunlight. At the same time, it emits the heat to deep space because this heat can penetrate through the atmosphere. So the overall energy balance, really, your surface lose heat, and hence it can be cooled below the ambient temperature, all right? So we made the nanocomposite using calcite nanoparticle, which is very cheap, comparable to commercial paint. And this is the SEM image. You can see the particle size there in a micron or a few hundred nanometers. So we confirm the performance by paying the P pattern. P stands for Purdue, actually, with our new nanocomposite, and the rest of the background with commercial paint. So under regular camera, you don't see anything because they both just look white. But under infrared camera, you can see the P is much cooler than the background. So which means that we can really cool the surface. It actually can be cooled even below the ambient temperature. So you get free refrigeration. And we have a full patent filed already, and the article is forthcoming on this. So we did also further analysis on the energy saving by using these radiative cooling paint surfaces as a pre-cooling coil for air conditioner. And we did this for Phoenix and the Reno. You can see there's baseline is without our system. And then we compare our two radiative cooling systems. We can save actually power for air conditioning for more than 75% in Phoenix and more than 80% in Reno. So we're working on a few more topics right now, such as color cooling composites, bio-inspired surfaces, and additive manufacturing of these surfaces, mass production of our product. We are working with companies on this, and the potential for addressing global warming and climate change, of course. So the sponsors, we appreciate our NSF Cooling Technology Research Center, Center for High Performance Buildings, and Office of Naval Research. Okay, second topic is thermal barrier coatings. We're looking at, again, this is the coating, but now we're looking at the turbine machineries. So in order to protect the metal blades, we need a coating with very low thermal conductivity as well as low thermal emissivity, so that the kind of it serves as a barrier to heat from the burning flames. So this is really important, and we have a new double project that for which I serve as a lead principal investigator and involve multiple Purdue faculty. This is gonna be launched very soon. So this team project involves many aspects of the project, includes multi-scale material design, advanced material synthesis of nanostructures, and high temperature characterizations of the properties as well as efficiencies. Okay. The third topic is, in order to design all those coatings, structures, and nanostructures, we need a multi-scale, multi-physics prediction capability. So this is sponsored by National Science Foundation, Air Force Office of Scientific Research, as well as Purdue High Performance Computing Center. So we're able to start with atomic structure of materials and cross all the scales to predict the thermal conductivity, thermal radiative properties, electrical properties, and so on. So one highlight I want to show here is, previously people only know 3 phonon scattering for heat conduction. And recently we developed new methodologies to include 4 phonon scattering, because these are the heat transfer mechanisms. So we developed the first method to do that, and the formalism and computational cost is very, very expensive. We need to use supercomputers to do this. But anyway, our work of 4 phonon scattering was considered as a breakthrough in the heat transfer modeling in recent years, and covered by many news media, and got nice remarks from our colleagues as well. So even better, a year later, after our prediction, a few groups made experimental breakthroughs. They published 3 papers on Science on boron arsenide. They all confirm the importance of 4 phonon scattering, which from our prediction. So this has become accepted knowledge now. It's being added to Wikipedia on the 4 phonon scattering. Okay, so the fourth topic I want to briefly cover is the machine learning energy systems. So this is a kind of a work together with our predictive methods. But even with the methods, sometimes you're facing extremely large design space. For example, we wanted to design a 20 nanometer long multi-layer structure with the lowest thermal conductivity, for like a thermal barrier coating or for thermoelectric material. But even for such a small structure, you have 30 billion possible configurations, and it's not practical to, check the performance of each structure one by one. So you might think that, okay, what about I use my intuition to search like a small fraction? But in that case, you might often be trapped with a local optimum, right? The global optimum might be well in your unexplored space. So we need to deal with that. So in my group, we have been using a genetic algorithm to find the optimum by only searching a small fraction. For example, you can see we start with a very bad structure, and then it evolves it's like a natural evolution, evolves to the best configuration at the end, which has the maximum performance. We even can find that sometimes the performance might be exceptional. We find, or the machine learning random structure can have even higher thermal activity than the periodic structure, which was surprising and completely changed the mindset of the community. So at the end, I want to mention a little bit our team. So we have a very diverse and strong current students in my group. We have National Science Foundation graduate fellowship winners. We have NASA Space Technology graduate fellowship winners, as well as other Purdue fellowship winners, and so on. So our group alumni included quite a few who joined tenure track faculty positions, and those who joined national labs, those who joined industry, including leading companies, or even co-founder of a startup company, as well as a few in postdoc who are in the pipeline for faculty. So on the right, you can see a few nice remarks from my students about the mentoring of our group. So, okay, that's all from me. Thank you. I think next, Professor Shweta Singh, you can go ahead and present. You can share your screen and unmute yourself.
Can you see my screen now?
Yes.
Let me try to go on the, so can you see the presentation?
Yes.
Okay. All right, so thank you very much for your nice talk. So I have a very short presentation. I try to keep it small.
Sure.
So thank you so much. So I'm going to talk about industrial ecology and sustainability assessment for emerging energy systems. So in brief, I will try to introduce why we focus on energy system. We do in our lab, we focus on a lot of different types of systems like ecological systems and how the ecological systems interact with industrial systems as well. But I'll focus only on the energy systems part and research on that aspect. So why do we want to study energy? Because we are talking about greenhouse gas emission and global warming, as Professor Ruan already talked about, that there is a lot of global warming happening and snow melting. So renewable energy is one way where we can reduce the greenhouse gas emissions, and that way we can contribute through the advancement of technology to reduce the global warming that is happening. So one thing that when we looked at the portfolio of energy, renewable energy across the globe, US, even though we are not very aggressive in transitioning our energy systems to our renewable, we still are at the second place in terms of installed wind capacity only. So when we talk about top 5 wind energy producers, we are among the second. In terms of our renewable energy consumption, however, this is 2019, this data came out in 2020, so it covers about 2019 consumption data. And this is from the EIA website. And you can see that the renewable energy portfolio is only about 11%. So out of which we have 24% wind and solar is just 9%, so that leaves us a lot of opportunities to transition from higher CO2 fuels or higher CO2 sources to renewable energy sources. So that's an opportunity for us as a country and globally to contribute to reducing the global warming potential. But when we are talking about changing from 11% to say 50% or 60%, that means that we are talking about a lot of energy infrastructure development and energy infrastructure change. And that does not mean that it is only has a local impact. It has a wider economic effect. It has employment opportunities. It might also affect some sectors negatively. And then there are also material and energy investments that will go into to build infrastructure, and then the operations and maintenance. So in our group, we take this systems thinking and holistic thinking approach, that we are not only going to solve the technology issue by looking at a narrow system boundary and just solve that problem, but really looking into the wider scope before we move forward with large scale changes, because we don't want to do something that can have unintended consequences. And that has been the challenge in the past. When people introduce DDT in the environment, they were killing the pest, but it also had an effect on birds and ecosystem. So we take the systems thinking approach, and that's where we use so our research question in our group focuses on that: how do we analyze the impact of expansion of renewable energy to make informed decision and avoid any unintended impacts? But it's not only for energy systems, we can do it for biological systems and other kind of manufacturing like pharmaceutical or energetic materials. So for that, we use the tools and computational methods that are available in this field of industrial ecology. So what industrial ecology thinks is that just like ecosystems, our industrial systems form a kind of ecosystem. So there is interdependency and there are connections that are in between these systems. So when you make changes to one part of the system, which is a subcomponent, you also have these indirect impacts. So industrial ecology over the years, over the past 20 to 25 years, has developed methods and tools that we can systematically use to analyze different forms of emerging technologies and also inform the design. So at a macro scale, we are looking at how this one small component change can affect the whole wider system. But then you can take that feedback loop and bring it back into improving your design and improving your decision making. So for that, there are different tools. One is life cycle assessment. So we do focus a lot on life cycle assessment, and currently we're doing most of the LCA we're starting a project on informing the novel energetic material design, which will have impact on energy consumption as well. Then we do this input-output based macroeconomic assessment. So input-output is basically a macroeconomic model that captures how different industries in the nation or a sub-regional scale interact with each other. So since it's a very large system model, our smallest model that we look at is it's a matrix kind of model, and we look at 425 by 425 different interactions. So when we start looking at much disaggregation, we get to 1000 by 1000. So it's a really computationally intense model. So what we do is that we use this virtual industrial ecology lab, which is a cloud-based system. There we have developed methods in collaboration with University of Sydney to analyze these macroeconomic assessment methods. And I'll show one of the results using that computational lab. And the last one is physical input-output model. So instead of just looking at the economic exchanges in terms of economic flows, we can also think of this economy as a biophysical system, because what we are thinking is we are thinking different processes, transforming different raw materials into resources, and then finally converting into products. So we also develop these physical input-output tables. So using that input-output model, we have done a simple analysis of what will happen if we installed new wind energy capacity in, say, top 10 states of United States. So the figure 1B shows the states where we have installed. So we have simulated, we have not installed. So we all do simulation results, right? We do not have the capacity to do that large scale installation ourselves. But so through the simulation in those 10 states, what we show is that in the figure 1A, you can see the indirect impact. So because of those 10 states expanding wind energy, we saw that about $3 billion of more economic activity also happened in the other states of the United States. Then the next thing we look at is our sectoral impact. So not only the energy sector is being affected, but also the metal manufacturing sector, because when you're thinking of new energy infrastructure, there is a lot of manufacturing happening. And when the metal manufacturing happens, it is very energy intensive. So if we did not take care of cleaning the metal manufacturing sector, we might see spike or instantaneous spike in CO2 emission for the short term. So through this analysis, we can show that which particular region is going to increase its CO2 emission for supporting the renewable energy expansion. Our future analysis will look into how can we redesign some of these manufacturing sector to reduce the CO2 emissions. So that's only short result, but some of the open questions around transition to renewable energy is reliability and uncertainty. So a lot of the challenges and obstacles in renewable energy adoption is that, is it reliable? Can we scale it up? Can we scale it up for the consumption level we are thinking about for the growth? And then also the end of life. We know that the photovoltaic and wind energy do not last forever. These infrastructures expire in about 20 years and they create tons of waste. So for that, we use something from industrial ecology, which we call as industrial symbiosis, similar to ecosystems, that how can industries have developed this symbiotic relationship and optimize the flows to reutilize all these waste. And then also critical material supply. So we know that United States does not have cobalt and nickel reserves, and all the renewable energy technologies and the batteries and infrastructure depends on these critical materials. So we are also working on mapping these supply chains to be able to understand what will be the sustainability challenges to scale up renewable energy. So that's about research. So I would like to thank, most importantly, all my graduate students. So there was a visiting graduate student from University of Sydney with whom we worked on the computational industrial ecology lab, and all my current graduate students, and also the sponsors, the Army Research Lab and National Science Foundation. And with that, I would like to thank you and take any questions.
Thank you very much. Next, Rakesh, please.
Yeah, just 1 second, I'm trying to share my screen.
Sure. Yeah, we can see the screen.
Can you see a complete screen or just a portion of it?
I think, we can see.
Okay, now it is okay.
Yep.
Now I think it's okay.
Mm-hmm.
All right. Okay, so like I'm a chemical engineer. and my name is Rakesh Agarwal, and what I'm going to do is describe to you some of the research which is being done in chemical engineering towards the sustainable energy. You heard both Professor Singh and Professor Wan telling you about the renewable economy, and then Professor Singh also talked to you about the recycling of the photovoltaics at the end of 20 years and so forth. So I'm on the other end. We are at the end where we are making photovoltaics actually, and creating that 20-year life cycle waste or whatever you need to manage. So with that preamble, what do we do? Like basically, what we are trying to do is like create an economy like whereby the everything lives off the solar energy. So like as Professor Singh just told you that 11% of the total energy is like, and she told you that the photovoltaic was a very small fraction of that. But then nevertheless, we do believe that at the end of the human race, like, you know, for majority of its existence for hundreds of thousands of years, like the human race has lived off the solar energy because all the biomass and biofuels and so forth. Similarly, going forward, 1,000 years from now, everything will live off the solar energy. That's the only way which can sustain all our needs. So we are imagining, if I may use that word, how we meet all our needs from the basic things like wind energy, solar, and the soil, which is water.
Okay, somehow I lost the song. I don't know, just myself or everybody. Can you hear
Okay,
still?
all right, sorry. Yes, I think my cell phone decided to shut me off. Okay, sorry.
Okay.
Thank you.
It's okay. It's okay.
Sure. Okay, so we are looking into how we will make all the food and all things, and then same thing about the hydrogen, and you have Nikola trucks. You folks must have heard about that. But hydrogen, we do believe not only for the chemical conversions, but it will be needed to support some other infrastructure like storage, electricity, and so forth. And how would we harness the electricity? How would we get our heat? And from there, how do we make all our chemicals, the fertilizers, the ammonias, the ureas, and how do we grow our food and make all our chemicals, the clothes and everything? How do we store the energy? And how do we purify the water? So the entire economy. So basically what we are after is how would we meet all our entire economy. So with that, like I'm going to skip. I don't know, I happened to pick up the wrong deck. I don't know what happened. I just opened so I'm going to skip, sorry for that. My apologies. Okay, so what we are doing is we make solar cells. So one of the big research we do is try to make the roll-to-roll processing. So a typical solar cell, for example, and we are making inorganic solar cells, which is stable for hopefully for 25, 30 years, not just 20 years. So our hope is that they will be stable for a long time. And here's a typical solar cell, like, you know, what you see here is they have many layers. And the thickness of these layers is very small, like 1 micron to 2 micrometer. In case you're wondering what is 1 micrometer thick, it is like 1/50th the thickness of your hair. So these are very tiny layers, like some layers are only 100 nanometers or 200 nanometers thick, and there's so many of them. And generally what happens to solar cells of these kinds, like the inorganic ones, are made by ultra-high vacuum, very high energy intensity, and so forth. But what we are trying to do in my lab is just print these solar cells, okay? And for that, what we are using is we're requiring a lot of chemical engineering knowledge, but along with that, like we collaborate, and you heard from Professor Shilin that how he's collaborating with a lot of different groups and so forth. Same thing in my group. We collaborate with physics, chemistry, electrical engineering, material science, all across the campus, and in order to make these, because it involves a lot of physics and chemistry and chemical engineering. So the vision is here. We do print the solar cells, as you see, slot die coating. So we have a slot die coater in the lab. We print the material, then we selenize, we grow the grains, and the whole idea is put all those layers which you saw through chemical back depositions and by spraying and so forth, and ultimately get the solar cell. So it's like printing. So the vision is to print it just like newspaper, so that we can put it everywhere, wherever we can see. So that's the goal actually of the group. And my group, for example, like just to give you an idea, so we have made 15% efficient solar cell in my lab, and we continue to improve. We have to, and just so the new graduate students will be joining the group. We are looking forward to make 20% efficient solar cells. So the day we have 20%, they can be deployed on a massive scale actually. But and so that's the intense research going on in my lab. Okay, with that, like the other item I wanted to quickly discuss with you folks is, which is a project we started 3 years ago, and that is how to use the, I'm going to skip again, okay, sorry for this Yes. Okay. So the question is, how do we use the land which is around to harness electricity? And so if we did do detailed calculations, we very quickly find out, like for example, in the state of Indiana, where we live, there isn't enough land area to put the photovoltaic and meet the Indiana's needs. So what that means is somewhere along the line, as the human race progresses, there will be a competition between the food and energy. And in order to avoid the competition between food and energy, we have been studying the use of photovoltaics on the agricultural lands and grow food at the same time while producing electricity. And the idea is that if you just install normal solar cells, what happens is they cast shadows. You can see the shadows here. And because of the shadows, the food yield goes down. So our goal is to understand all this behavior and come up with the solar cell designs and their operations so that the solar photons can be synergistically shared between the food and the energy, and the food yield should not go down. So we have begun to do. So this is actually from the Purdue's acre farm, which is what we built last year, and you can see that we did grow corn. And so this is quite an exciting project, by the way. This is our system for food, energy, water, and we have been collecting data again this summer. So actually, on Wednesday we are going to go and harvest our second yield of the crops. Okay, so and what we do is we collect data on 2,000 plants, handpicked for their yield and height and so forth. So it's quite an exciting project actually, which is what we are doing. And our ultimate vision, where are we heading? So where we are heading is that if you think of the human race, like what locally on the farm, produce the wind and the electricities and purify the water, do a drip irrigation, produce your chemicals, locally produce the chemicals, and then locally. And here's the urban areas, you provide them hydrogen, food, pure water, batteries, energy storage, everything together. So our vision is how to make local photons for local needs. Okay, that's the goal. And so the students in my group, that's what they do research on. And we do a lot of modeling, by the way, which is I just basically touched. So as a matter of fact, the PV eclectic farming, which I showed you came out of the modeling that we need that, okay? Because before we went and we built it, we want to make sure that what we are doing really makes sense, and that's what we did. Okay, so with that, here's my group, okay, of the students who have been doing research on modeling to experiment. And in the interest of time, I would stop and I will just show you a sunrise on our PV eclectic farm. So I just wanted to leave you with a physical image of a beautiful sunrise early in the morning, like when we walked to the field, and you can see the corn growing and in the background of the PV cell. That's all I have, Juan.
Sure. Yeah. Thank you very much. It's great. So students, please feel free to type your questions in the chat box, or after we've done the last presentation, you can also unmute yourself to ask questions. So now, Professor Rebecca Sees, your turn.
Sure. Can you see my screen?
Yes.
Okay, great. So as has been said, I do a lot of systems interactions to really identify how energy technologies, economics, and decision-making interact to drive energy system changes. And so this is just a plot showing some different warming scenarios through the end of this century, depending on how much net CO2 we continue to emit. And so at the top, you can see these really, really high warming scenarios where we're continuing to pump a lot of carbon into the air. Below those are some 3 to 4 degree scenarios, which may be where we're at if you consider some of the more recent policy changes and implementation of more renewable energy and more fuel efficient technologies. But if you really want to get to these low warming scenarios, the 2 degrees scenarios or less, overall emissions have to drop to 0 or even become negative by somewhere around mid-century. And so how do we actually identify the best way to go about that? And so most of my research is identifying the technology trade-offs from engineering principles, modeling market adoption, and then identifying who's making decisions about energy technologies and what kind of biases or heuristics do they use in the decision-making process to really identify what the decision space in these different applications is. And so most of my research to date has been related to lithium ion batteries. And so just before I start talking about some specific projects, I figured I would talk a little bit about lithium ion batteries 101. So every lithium ion battery is called a lithium ion battery because lithium ions are the charge carrier. There are different materials used for both the positive and negative electrodes. And there's been a lot of innovation in this space to try and reduce the cost of those materials and store more energy within them. And so energy density and other factors that you kind of define batteries is really defined by that materials research. There's also the design aspect of batteries to consider. And so there's only a handful of different formats that batteries can be made in, whether you've got these big pouch cells or these cylindrical cells that are much smaller, and they're things that are used in like the Tesla vehicles. And so a lot of my research has been looking at how these different design changes impact the overall life cycle of batteries. So the one project I worked on was looking at the environmental impacts of lithium-ion battery recycling. And so looking at how those different anode and cathode materials impact the emissions from the recycling process, as well as which recycling process you actually use and where we can identify new areas for innovation. I also did some research looking at how you would potentially redesign a lithium-ion battery if you know that you're going to use it for a long duration application. That might simplify some of the design constraints on how fast you can charge and discharge a cell. And so having a simplified model to assess how lithium is transferred within the battery pack, within the cells themselves, and then looking at a systems level, how does that impact the overall cost of a battery when you change these different design parameters? And so we can see that shifting to reduced power demand batteries enables thicker and thicker electrodes, and so you can reduce manufacturing costs in that way. And so since I'm a new professor here at Purdue, I figured it would be helpful to talk about some more ongoing and future projects. So looking at how materials and resource demand for decarbonized transportation pathways compares, whether you think that an electrified electric vehicle pathway with batteries or potentially with fuel cells, how do you develop lowest cost safe battery systems? And so there are different design choices you can make from a materials perspective, but also from a systems level perspective when you've got the battery modules and packs. How to use dispatch storage technologies for stacked benefits. And so energy storage technologies can provide a lot of different resources for the grid at different time scales. And so whether that's at minute to minute, hour by hour, if you want to do real renewable load shifting, how do you best dispatch batteries in ways that they can both make money, but also to provide the most service to the grid and to the decarbonization effort. Evaluating decoupled power and energy storage costs. And then finally, so energy storage, and so that I've seen so far, is really effective at relatively short durations, but how do you bring in other aspects of our economy, so the industrial processes, to potentially contribute to the energy system as a whole, and provide seasonal arbitrage of different storage technologies that way. So with that, I would provide, so my group is very small. I have a handful of students, but I just started this semester. So there's some general resources about EEE and mechanical engineering, which are the two departments that I am appointed to.
Sure. Are we finished?
Yep.
Okay, great. Thank you very much, Rebecca. So now we can start the questions and answers section. But before that, I want to say that, this is a wonderful panel with professors from different departments, students also from different departments. So feel free to contact professors afterwards to schedule one-on-one meeting or email communication. So these are exciting projects. Okay, we're gonna start to look at question. Seems there is one question right now for myself. So can you talk about radiative cooling, paint efficiency, or local hotspots or not? So yeah, this is a passive radiative cooling, so it doesn't consume any power. We don't really talk about efficiency. Otherwise, you get the cooling without any power consumption, so that would be infinity. Because it sends the heat to the deep space, it doesn't create any hotspot around our coating, so the heat goes to the deep space. Yeah, thank you. Any other questions, please feel free to unmute yourself and ask any of the professors who are here. Please.
It seems you're very good in giving up presentations. Like,
Oh, okay, thank you.
This is Anna. I have a question that can apply to all of you. So you mentioned a few different areas of research within each of these groups. Can you explain how it works? Do students specialize in one area, or do students get to work on all of these initiatives?
Okay, let me suggest that we do a reverse order. We're gonna start with Professor Rebecca Sees. You go first.
Yeah, so I would say typically you would focus on one main project. You might collaborate and help. Typically you're within like a larger research group, and so you generally have like one or two projects that you're really leading, and you usually kind of collaborate and maybe help out and do some different analysis on areas you've got expertise in some of these other areas. So generally that's the path for graduate students.
Sure,
Yeah.
Professor Agarwal. Yeah.
yeah, so like in my group, like for any given topic, like so let's take as the example of making solar cells, solution process solar cells. So the student who joins, like that student generally would learn, like she would learn, like for example, like all the physics of making solar cells, and I interact very strongly with the electrical engineers. For example, right now there is a meeting going on of my group with the electrical engineers on campus, but I'm on the panel, so I'm not attending that. We have every week those meetings. And then similarly, I have collaborations with material science and as well as chemistry. So students do touch all the aspects. And certainly to make a solar cell, you need to know what a PN junction is, what the electronic device is, and so forth. But at the same time, they do specialize in one aspect. So for example, a student could specialize on the material side, like what material to be used, or some students specialize on the optoelectronic characterization side as to like modeling of the solar cells and looking at the defect densities and finding all those out. So what I would say is that generally a student spends the first 1 or 2 years learning all aspects, but the last 3 years mostly picks an aspect where it spends 80% of the time, and then 20% of the time interacts with other graduate students and other professors to move the project. And that is also true for PV electric farming, meaning like the students would take a course in agriculture, learn how the plants grow, how they share the photons, what are the 2 cycles for the food making and so forth, and at the same time do like a lot of modeling between the interaction between the photons and the solar cells and the plants. So, but then the student does a very intense modeling, for example, on the shadows and how the PV should operate, but at the same time analyze the plant. So it's a knowledge in a little bit of all, but specialization in one area in depth. So that's how I describe it.
Sure, thank you. Professor Singh, anything to add? Mm-hmm.
Yeah, so I think it's in my group, the model is same as Professor Agrawal. So in what students do in my group is that they get familiarity with all the different kind of modeling techniques for sustainability assessment. So life cycle assessment, industrial ecology tool, system dynamics, agent-based model. So there are multiple tools that you can use, and it's the question that you ask. So it's basically in the first 2 years, they get familiarity, they do small projects, and then they pick up their own specialized topic of their interest. So some students are very passionate about energy systems, so they would study renewable energy and future energy infrastructure. Some students are more passionate about recycling, so I have students focusing on phosphorus recycling and nitrogen recycling, basically on the agricultural side, and human waste and animal waste. But then there are also students who are very interested in critical materials. I have one student who is working with Argonne National Lab on cobalt and nickel. So since the modeling techniques are same, people get familiarity and foundation, very strong foundation on those, and then they pick the topic of interest. And it also depends on what the student's career goals are, if they like what kind of career they want to pursue, industrial versus academic or something like that.
Right.
And that becomes more clear towards the end of your graduate program.
Yeah, so I agree with all that has been said. I just want to add one more point. In my group, we do both modeling and experiment. We do have collaboration, and we encourage collaboration between the students who are doing experiment and the model. So one can explain the other, or one can be validated by the other. So that's certainly that's amazing. Okay, thank you.
Great.
So I see one question from the, okay, Anna, do you have anything to add more?
No, just wanted to say thank you.
Sure, thank you. So I see one question in the chat box. Probably I can combine the two. Can you talk about different track of the students, or how do you prefer PhD or master students? I would say that, okay, we can start from me. Yeah, I do prefer PhD students, depending on the projects, but I do have a small fraction of projects that might be appropriate for master students as well. So if you look at my group right now, I have both PhD students and the master students, and they are funded. So, okay, that's from my group. Professor Sink, do you want to say something about how you're hiring and so on?
Yes. So yeah, we also prefer PhD students mostly because, as we said, that in the first couple of years, you're only getting familiar with the computational tools and getting familiarity with the methods. So the master's project are really small. I do have one master's student, so that project is really applied and solved. But if you really want to get into the theoretical and conceptual contribution to the field, I do hire PhD students.
Yeah, Professor Agarwal?
Yeah, same thing here. Actually, because in my group also, we take only the PhD students. Masters is rare. I have had some masters students, but they're very rare because of the reasons which processing just elucidated very well, in the sense that it takes a while to learn and begin to contribute. And regarding the tracks, different tracks for the graduate students, well, just like what Professor Wan said, the modeling tracks, and there are chemistry tracks, oriented tracks, and there are material science oriented tracks. And so in my group, students who come, those who want to do modeling, they spend a lot of time with modeling. And in rare situations, I have had students who did both, who did experiments and modeling. That doesn't happen that often, though. I would say I would say that every fifth or the sixth student is like that, who comes to me and says, she or he wants to do both. And when that happens, I agree with Professor Ron. That's absolutely a fabulous case, because a lot of synergies exist between the two, and they can truly take advantage of the synergies. So, and just for the completeness sake, in the chemical engineering as a whole, there are many tracks for PhD. So we have a catalysis group, people who get the PhD in catalysis. There are people who they get on the biomedical side of the track, and they get degrees in the biomedical. Same thing about the biochemical. Same thing about separations. Okay, like chemical separations. I happen to be one of them who works in separations in that team. And then we have a track on pharmaceutical, and you heard Professor Singh talking about the energetic materials. So in my department, there's a track on the energetic materials also. So there are various tracks, and depends on the individual's interest when they join the chemical engineering department. I would like to say, in a sense, that we are like a supermarket, like a Walmart. You go on an aisle, you can find the cereal of the flavor you like. Okay, it is the same thing for I would say not only chemical engineering, for all the departments on the campus. Purdue is a big university. And so I would not worry about the tracks as much as what your interests are. I can guarantee you that you will always find an expert of world-known authority in the subject at Purdue to work with. Okay, he or she, you will find it.
Sure, that's great. Yeah, I totally agree. Thank you. So Professor Seeds, anything?
Yeah, so I would definitely agree with what's been said. It's definitely, in terms of funding and support, it's definitely easier if you're looking at PhD students, just because it does take a long time to build up the knowledge and really get a deep dive on a project. This is definitely like a research-focused presentation, but there are other, if you don't necessarily want to stay in research for forever, there are different master's tracks, whether it's a professional, whether it's a thesis, and so those are definitely available if you don't want to do the full PhD. It's just a little bit more tricky to try and find financial support.
Sure. Thank you very much. I think I already got an indicator from Stephanie. The time is up. So I have one quick question. Can we apply to spring and the fall? I think in ME, we have both spring and the fall admissions, and you can look at the spring 2021 deadline already passed, but I sometimes we give a little bit grace period. Please check with the grad office if you're interested. I think probably other schools do spring and the fall as well, if I'm not wrong.
Yes.
Yeah.
Yes,
I think Triple E is the only exception. It only has like one main cycle.
Okay, great. Well, with that, again, I want to emphasize that please do feel free to email and contact all these professors if you have interest in their projects. So because of the time is so limited, we have to stop now. Okay, thank you very much. Thank you all for the speakers as well. Okay, you have a great day.